Hi, so in this video we're going to do one more of the long answer questions from the 2016 Maths Admissions Test. If you're watching these as I'm uploading them, then I know it's only a day or two away, so hopefully this will be useful for you, or perhaps you're watching this in future years, in which case my guess is the exam won't be changing too much anytime soon. Question 3 here from 2016. Again, I'm just going to work through this and I'll write up all the answers as if as much as possible as if this would be how we do it in a real exam. You may want to be very slightly more thorough than things that I write here, but we'll see. Okay, so we've got a definition in this question, which is that a function is bilateral if f of x equals f of 2 alpha minus x for all x, where we're considering alpha as a fixed number. So bilateral here isn't meant to be something you've come across before. It's a definition that you're given, and they're just testing whether you can work with, you know, something new, something that's been defined for you. Just apply the definition, see what the consequences are. Okay, so we won't worry about what bilateral really means. We'll just use it. So part 1 here, it says show that if f of x equals x minus alpha squared, then the function x is bilateral. Okay, so what we need to do is to show that the definition is satisfied. So we look at f of 2 alpha minus x, and the function here is x minus alpha. So I will take this as my x, so I get 2 alpha minus x, and then I subtract alpha, and then I square it. Okay, so 2 alpha minus alpha is alpha, so that's alpha minus x squared. That's not quite the same as f of x here, but of course alpha minus x squared is the same thing as x minus alpha squared, because when you square the negative of a number, you get the same thing as when you square the original number, and that is equal to f of x. So we can say that f is bilateral. It satisfies the definition that we've been given. Okay, so in part 2 it says, on the other hand, show that if f of x equals x minus alpha for all x, then it's not bilateral. So we do the same thing. We'll look at f of 2 alpha minus x. So take this as our x and subtract alpha. Then it'd perhaps be nicer if they'd given these different names here or something, but it's fine. 2 alpha minus alpha is alpha minus x. Well, this is exactly minus x minus alpha, which is minus f of x. So this one, in this case, f is not bilateral because it doesn't satisfy the definition. You know, these two things are not going to be the same. And this isn't going to be the same as f of x unless f of x is 0 for all values of x, but it's not because it's equal to x minus alpha. Okay, so don't think we need to spell it out too much. You might make some comment about 0, but I think you get the marks there. So part 3, it says show that if show that if n is a non-negative integer and a and b are any real numbers, then integral from a to b of x to the n is minus the integral from a to b of x to the n. And I think this is just straightforward crunching out of the integrals here. So integral between a and b of x to the n dx, that would be x to the n plus 1 divided by n plus 1 between a and b, so that's b to the n plus 1 over n plus 1 minus a to the n plus 1 divided by n plus 1. Whereas if we look at the other side here, we've got minus the integral from a to b of x to the n, minus the integral from b to a of x to the n. That's minus, it's the same thing here, but we've got the limits reversed, so I get minus a to the n plus 1 over n plus 1 minus b to the n plus 1 over n plus 1, which is just the same thing as we had above when we expand the brackets. So I think we're done now. So very easy, that part, but I guess this must be building up towards something else. So part 4, it says, hence show that if f is a polynomial, then the integral between a and b of f of x dx is minus the integral from a to b of f of x dx. So we need to show this is true for any polynomial, and it's sort of obviously true, I suppose. But once you've proved this, I mean, if I take any polynomial f, that means I can write it as a0 plus a1 times x plus a2 times x squared up to sort of ak times x to the k. So if I were to integrate this polynomial from a to b, that would be the integral from a to b of a0 plus a1x plus a2x squared all the way up to ak x to the k dx. And I could split this integral by linearity into a series of integrals a0, a and b times the integral of 1 dx plus the integral between plus a1 times the integral of x plus a2 times the integral of x squared all the way up to ak times the integral of xk, and we should all have dx's. And then, by part 3, these are all equal to, all of these integrals are equal to minus the same thing with the a and the b reversed, minus a1 times this integral minus a2 times the integral of x squared with the limits reversed all the way up to minus ak times the integral with these limits reversed. Okay, and then again I could put these all back into a single integral now, so that's the integral, it's minus the integral between a and b of a0 plus a1x plus a2 x squared all the way up to ak times x to the k dx. And this thing I've got in here now is just the polynomial f of x that we started with. So we've proved that if it's true for any individual of the this result is true for individually for each of the terms in the polynomial, then it's also true overall for the full polynomial. And so it's really a question of just writing this out carefully. If you're confident with your summing series notation and things, you might find a more efficient way of writing this out by starting by saying that if you started by saying f of x is equal to this sum from, I could say it's the sum from I equals 0 to k or something of ai times x to the I, where the first term x to the 0 is just 1, and I could kind of do it all at once here. I could say the integral of f of x dx. We need a new pen. The integral of f of x dx here is just the integral of this whole thing, and then essentially what we're doing here is saying we can swap the order of summation and integration, so that's the sum of the integrals, and then you can use the result. That was from a to b, and you can use the result. Okay, I could pull out the constants as well, and use the result from the previous part to say that's the sum of minus ai times the integral written the other way around. I think I've no, that's okay. So I changed the integral from a to b. This is exactly the same thing as we've done above, just and now I say, okay, that's the same as the integral of the sum of minus ai x to the I dx between b and a, which again is minus the integral of f of x dx from b to a. Sorry, I've got a bit messy down here, but my point is, if you want to just write this polynomial as a sum instead of doing it one term at a time, you can come up with a slightly cleaner argument, although I haven't written it very cleanly there because I was rushing a little bit. Okay, but anyway, we've proven the result, so let's move on. Part 4 we've just done. So part 5, it says suppose that f is any bilateral function, so we can use our definition again earlier, that bilateral, remember, meant that f of x is f of 2 alpha minus x. It says, by considering the area under the graph of y equals f of x, explain why for any t greater than or equal to alpha, we have the integral between alpha and t of f of x is equal to the integral of between alpha and 2 alpha minus t. And I think the thing to notice here is that because f of x is the same as f of 2 alpha minus x, if we just think about the graph of this function, it's going to have a line of symmetry, whatever this function looks like. I've made it difficult for myself to draw it, but it's going to have a line of symmetry around x equals alpha. Okay. Because if you imagine putting in, let's take something that's slightly bigger than alpha. So let's say I take alpha plus c, right, and I do f of 2 alpha, then minus alpha plus c. That's f of that should be in brackets. 2 alpha minus alpha, so that's f of alpha minus c. Okay, and this first thing here, because it's a bilateral function, well, f of 2 alpha minus x is the same thing as f of x. Okay, so this is also the same thing as just f of alpha plus c. Okay, so the definition here implies that f of alpha plus c is the same as f of alpha minus c, which means I have a line of symmetry, x equals alpha. Right? So why does that give us this thing here? So if we take t greater than or equal to alpha, so let's now take this, rather than having this as alpha plus c, let's draw a function out again around alpha. Let me just make it anything it's meant to be symmetric about alpha, and so I go to, so if I'm going to integrate from alpha up to t of the function, okay, so that means going up to here, right, that would be this area here, and 2 times alpha minus t, well, this distance here is t minus alpha. Okay, so if I do alpha minus t minus alpha, that's alpha minus minus alpha, that's 2 alpha minus t. So if I go the same distance the other side here, I get to a point 2 alpha minus t. Okay, so actually this area here would be the integral between of f of x between 2 alpha minus t and alpha of f of x dx, and we can say those two are the same because by symmetry they represent equal areas on the graph. Okay, so it does tell you by considering the area under the graph, so an argument like this based on the picture is going to be fine so long as it's clearly presented. Okay, so if f is a function, then we would write g for the function determined by g of t is equal to the integral between alpha and t of f of x dx. and now we suppose that f is a bilateral polynomial. We want to show that g of t is equal to minus g of 2 alpha minus t. Okay, so we notice when we look at this question that we've got 2 alpha minus t here that was in the limit here, and we've just done that part of the question. Looks very much like we're just going to use the previous result. Look, we've got g of t is exactly the thing that we've defined here, and we've just proved a result that says that's equal to something else that involves something that looks like what we're going for. Okay, so we're going to try and piece these things together, and we'll just start then with saying, okay, g of t, that's equal to the integral between alpha and t of f of x dx, which by part 5 here is equal to the integral between 2 alpha minus t and alpha of f of x dx. Now that's not quite the definition of g of 2 alpha minus t. For that we would have to have these limits reversed, and of course in the previous part, in part 4, we proved that if I take a polynomial and I want to reverse the limits, okay, right, all I have to do is put a minus sign in front of it. So if I change the limits, the whole thing becomes negative. And now this is exactly the definition of g of t, but instead of t, I've got 2 alpha minus t, so this is g of 2 alpha minus t, and that's exactly what we wanted to show. So we're done. Okay. And in the last part of the question, part 7, it says suppose f is a bilateral polynomial such that g is also bilateral, show that g of x equals 0 for all x. Okay, so g is bilateral, okay, means that it would satisfy the same that definition we started with. It had f in it before, but it's now got g in it, so that says that g of 2 alpha minus x is equal to g of x. Okay, but we also know that f is bilateral. Okay, and we showed that in part 6. Okay, showed that f being bilateral meant that g of x, okay, I've called it, you could replace x with t here or t with x, doesn't matter, showed that g of t is equal to minus g of 2 alpha minus t, so let's write x in place of t here. It said that minus g of 2 alpha minus x is equal to g of x. Okay, and these statements will be true for all x, right? Well, these two things are both equal to g of x, but they're also equal, so it's g of x is equal to this thing, but it's also equal to minus this thing, right? So that means that g of x equals minus g of x for all x, right? And the only way that something can be equal to its negative is if it's 0, right? Every other number is not equal to its negative apart from 0. Okay, so that means that g of x could only be equal to 0. So it's the 0 function. Okay, so we've just applied the definitions and come to the conclusion that we wanted to. So, I mean, this is kind of an interesting question because it's much more in the style of also of what you can expect in some parts of university level maths, especially when you come to study analysis, something called analysis, which is a little bit different in style to what you're used to at A level perhaps, which is why they ask these questions. Okay, it's a test of picking up new definitions, being logical, being rigorous, being thorough. Sometimes feels like you haven't done a whole lot when you answer one of these questions. The results, when they come out, can seem like they're maybe not hugely interesting. There's not a huge amount of depth to them, but the real skill is about being precise, logical, clear, concise, all of those things, and writing your answers, and showing very clearly why these statements are true. Okay, I quite like those sorts of questions. Hopefully that was interesting and useful. Good luck with the exam if you're sitting it sometime soon, and this will almost certainly be the last video I'll put out before the 2017 math exam, but if you're doing this in future years, hopefully I'll make a few more. in time for those ones. Okay, good luck with the exams, and keep watching the videos. All of the videos I've made are also indexed at the Mathsaurus website, so check that out and share it with anyone else who you know might be preparing for these exams, or for GCSE or A-level exams. There's lots of content on there for those as well, and a few step questions which I'll keep looking at as well as the year goes on.